We start off with the first chapter. This is a chapter about representing motion, or its qualitative description of motion. I'm not going to spend much time on this chapter. I would urge you to take a good look at it. It is a very readable chapter, and definitely review this. I'll just highlight some features about this chapter. But before we get to that, let's just introduce the subject that we are going to be discussing. As the title suggests, we're talking about motion. So a recurring theme, in fact, in this course, is going to be motion. Okay. And the aim is to provide, let me just say, provide a mathematical description of motion. And in order to provide a mathematical description, what we would need is, let's make it a little thicker, to define, obviously, mathematical quantities, to define mathematical, or these are also called, or physical, that means something that you can measure, quantities. As it turns out, in the study of motion, there are three fundamental, or basic quantities. And these are, again, we're talking about object moving, moving from one point to another in time. So obviously the first one would be time. And as I introduce these quantities, I'll talk about the units that we use to measure these quantities. Well, the units are, you can have seconds or minutes or hours or days and so on, years and so on and so forth. Another quantity, an object is moving from one position to another. So obviously we need to measure the position of an object. And the units on position, of course, are, you can measure it in meters, kilometers. You start with a reference point and say how far that object is from the reference point. So meters, kilometers, miles, centimeters, and so on. There are different units as well. And the third quantity, which is not going to show up right now, but later on in the semester, we will be introducing this one as well, is this notion called mass. And let me just say, for now, we're not going to be worrying about it. This will come up later. And the unit, there are various units to measure mass. There's kilograms, grams. You might say a pound, and I'll put that in quotes because technically pound is not quite a unit of mass, but well, I'll leave it out there. Or an ounce and so on. Okay, now of all these units, now, one can choose any set of units to measure these quantities, but we just decide on a convention or a standard set of units. So we just agree upon a standard set of units. And in the physical sciences, or in the physical sciences, the preferred set of units are these: time measured in seconds, position in meters, and mass in kilograms. And in fact, these set of units are called the SI units. And these are the preferred units in the physical sciences. Okay, Now, again, coming back, so this is just an introduction of motion. Now, coming back to this chapter about representing motion. Well, one nice way or an intuitive or qualitative way of measuring or of understanding motion or describing motion is with what we call motion diagrams. So let me just say that this is more an intuitive or qualitative way of describing motion. Okay, involves these motion diagrams. So motion diagram. So what exactly is a motion diagram? So suppose you have a car moving on a road, and you've got a camera with you, and you start taking snapshots of the car at equal time intervals. So you start off, you take so this picture out here on the left, the car is out there, you take a picture, and you got it. Camera in the same spot, and you take another picture sometime later, the car is moved forward, and again, in equal time intervals. So let's say it is 1 second later, you take the picture, car is here. Now another second later, it's here. So at equal time intervals, you take a bunch of pictures of this moving object. Now what you do is you take all these pictures and you superpose them one on top of the other. And essentially now you end up with an image that looks like this. The same car at its position at equal time intervals. Okay, the same amount of, it says out here, the same amount of time elapses between each image and the next. So these are positions of the car at equal time intervals. And now just by looking at this picture, you can gain a lot of information about this moving car. Okay, for one thing that we notice is this car has moved equal distance and the same distance in equal time in equal time intervals. So you can say just by looking at this picture, hey, this car is moving at pretty much a constant speed. Okay, here is another image of a car. Again, remember these pictures are taken at equal time intervals, so which means what you're finding is as the car moves forward, it's covering shorter and shorter distances as it moves forward, which means here's a car that is slowing down or, probably eventually coming to a rest. Now, the fact that we're talking about a car is kind of immaterial out here, so you might as well represent the object by a bunch of dots. And this would be a motion diagram. And this would be a motion diagram of an object which is in some sense slowing down. Okay, so by just looking at these pictures, you can gain that information. And here are some other examples of, this is another example of an object which is moving down, but as it moves down, notice in equal time interval, it is covering greater and greater distances, which means here is an object that is moving down and speeding up as it moves down. Okay, its speed is increasing. Now, one thing that I forgot to mention when I talked about the fundamental quantities, notice as I was looking, when we were talking about motion diagrams, we started talking about speeds, and you might say, well, where is speed in this? Well, as it turns out, once you have, that's why we call these quantities the fundamental or basic quantities, because once you have them, the other physical quantities that we need, that we require to describe motion, can all be built from these physical quantities. Okay, so they are not fundamental, they are in some sense derived quantities. Like speed is a derived quantity. Later on we'll talk about acceleration, again another derived quantity. We'll talk about forces, again a derived quantity. Okay, sorry about that for moving away, but coming back to motion diagrams. So motion diagrams is one way of describing motion, understanding the motion of objects. Okay, here's a question that you have. You've got two joggers running, and you're looking at the motion diagrams of the two joggers. There are jogger A and jogger B. Okay, and again, you're taking snapshots of these joggers at equal time intervals. And what you find, and from this picture, the question is which runner is moving faster? And I'll give you some time to think about it before I give you the answer. Okay, so just looking at this picture, you can see that the jogger A is covering a larger distance in the same amount of time. okay, as you can see from the sketch. And so what you have here is just by looking at these distances, you can see that, which means from the sketch, you can say, well, it must be jogger A who is moving. It's the runner A who's moving faster. Here's another question. Two joggers jog along a track. The times at each position are shown. Which runner is moving faster? Again, I'm just giving you some time to think about it before I give the answer. Now here what you're seeing is when the camera which is taking pictures of runner A is actually taking two pictures for every one of the camera that's looking at runner B. In other words, if the camera taking pictures of runner A is taking a picture every second, while this is taking a picture every 2 seconds. Okay, having seen that, but then you notice that in 2 seconds, the two runners have traveled the same distance. So obviously, in this case, the two runners have the same speed. Okay. Here's a much more, a bit more involved. You're showing motion diagrams of 3 objects. One of them is that of a dust particle settling to the floor, another a ball dropped from a roof, and the third a rocket descending and making a soft landing on Mars. So which motion diagram corresponds to which object? Okay, here, as you can imagine, it's the dust particle, which is kind of floating and settling to the floor, must be moving at a constant speed, okay, is moving. In fact, you're even told that it's moving at a constant speed. Well, if it is settling to the floor, it must be moving at a constant speed. On the other hand, if you drop a ball from a roof of a building, as it falls, it's going to be speeding up. And when a rocket makes a soft landing, obviously, as it approaches the surface of Mars, it has to be slowing down, okay? Having said those 3, you will see that the motion diagrams corresponding to these objects are going to be C. In other words, A corresponds to a ball which is traveling faster and faster as it moves downward. B corresponds to an object that's moving, covering the same distance in equal time intervals, which means it must be the dust particle. And C corresponds to the rocket, which as it approaches the surface of Mars, it is slowing down. Okay, so that's how you can, that's the information that we can get from motion diagram. You don't get a lot of information, but you can say a lot about the motion of the object. Okay, that's the way you want to think about it. Okay, so having talked about motion diagrams, let's move on and now focus a bit more on these physical quantities that we talked about. Again, physical quantities are just mathematical quantities that we need in order to, in this case, we're trying to describe motion. There are, as it turns out, physical quantities can be classified into 2 groups, 2 separate groups. We call them either scalar quantities or vector quantities. Now, what's the difference? Well, scalar quantities are completely specified by what we call a magnitude. So scalar mathematical quantities, which are scalars, are completely specified by what we call a magnitude. What do we mean by magnitude? That means they're completely specified by a number plus, of course, some unit. Okay, so well, to make sure we understand this, let's look at some examples of what we could consider scalar quantities. Examples would be time. Say, if I'm in my room, and if I were to say I walk across my room, and it took me 3 seconds to walk across the room. It's not that large a room, but I'm walking slowly, so it takes 3 seconds. So I'm giving you a time of 3 seconds. So time, as it turns out, is what we call a scalar quantity. Or I could say the speed of a car is traveling, and it's traveling at 50 miles per hour. So speed is, when I say it's 50 miles per hour, that's another scalar quantity. You can say the height of an object is, a person's height is 2 meters. again, physical is a scalar quantity, or the temperature, the outside temperature is 20 degrees Celsius or 70 degrees Fahrenheit. Let's just stick to Fahrenheit scale. So, oops. So I say it's 70 degrees Fahrenheit. That's again a scalar quantity. So these are all scalar quantities. Or let me list one more. Mass of an object. A person's mass is 60 kilograms. Okay, completely specified by a number, 50 or 2 or 70, and a unit, miles per hour, meters, degrees Fahrenheit, kilograms. Okay. Now, what are vector quantities? Well, vector quantities are, in fact, quantities that are specified by, they still have a magnitude. But in addition to a magnitude, they also have a direction to them. So to completely specify a vector quantity, you need to assign a magnitude, which is a number plus a unit. That's what we mean by a magnitude, number plus a unit. But apart from that, we also need to specify a direction. So for example, I can say, let's say, I'm going to write down an example, and one of them is what we call a displacement. Now, how do I specify a displacement? Let's say, I'm going to write this. I walk 2 meters, and to this I also add another phrase, to the right. So assuming we know, we have decided on which side is right and what is left, and if I say I walk 2 meters to the right, I'm specifying a displacement, which is a vector quantity, because to complete it has two parts to it. There is a magnitude and a direction. Okay, another quantity would be a velocity. Well, here is another term you see in physics, velocity. So if I say velocity of a car is 50 miles per hour, and I add to this, to the west. Now here, let me pause here and make one thing very clear, and this you'll notice this frequently, that sometimes you see words that we often use, colloquially, or it's a common word, but in physics it has a very specific meaning. When I talked about speed, I said speed is a scalar quantity. Now, in common usage, ordinary usage, we use the words speed and velocity interchangeably. But in physics, speed is a scalar quantity. When I talk about the speed of an object, I just tell you what its speed is. When I talk about velocity, velocity has two parts to it. Yes, I'm telling you the speed of an object, but I also need to specify the direction in which the object is moving. So here I'm saying it's moving to the west. That tells you that I'm specifying the velocity. So if I were to say this velocity of a car is 50 miles per hour, and I do not include this term right here, if I do not include that, then that's an incorrect statement, a mathematically incorrect statement, because when I use the word velocity, I mean I'm talking about a vector quantity. So I have to include this little bit. I have to specify the direction as well. There are other quantities we can talk about. Well, we'll be talking about acceleration, okay, and we'll get to that later. And also maybe force. And again, force is also easy to understand. So here I've got, I'm in my room. I've got a table, and I'm going to push the table. I could push the table. If I push the table in the downward direction, obviously nothing happens to the table. It's on a floor, nothing happens to it. But if I push this table at an angle or along the side, on the edge, then the table starts moving. So when I'm pushing it, I'm exerting a force. Now, the way the table behaves depends a lot on which direction I'm applying the force. So you can see force is naturally a vector quantity, because depending on the direction, you get a different result. Okay, so these are vector quantities. So vector quantities are quantities which have both magnitude and direction. Okay.